my model of what's happening right now in AI is that we have figured out how do we build intelligence without understanding how it will work. Because we know this algorithm SGD, which is very simple, which we can run, and we have a bunch of data that we feed into it, and then we train the weights of a neural network, and then the weights will be somehow good at the task that we trained it on. But we will not understand why, like what is this algorithm that the neural network implements in some way? Like how does the reasoning work? We don't understand it at all, but we do understand how to get it. So we understand how to get powerful reasoning without understanding what are the internal mechanics of that sort of reasoning process. And then, well, it's really bad if we just manage to build an AGI with that because, well, we don't understand really anything about how this AI is reasoning and how it works. So, alternative approach is we just figure out how this reasoning works. Like, what is reasoning? Like, ideally, I want to be able to, like, yes, okay, now I understand reasoning. I can just write down a Python program. Like, here are all the steps. Like, just like if I write down quicksort, then I can be like, oh, look, yes, here I'm selecting the pivot element. Here I'm selecting all the elements that are smaller than the pivot element. And so, like you can walk through the algorithm, you can see what's going on. I want to do it such that the algorithm of intelligence for reasoning, I know how to write it down this way. If I have like the step-by-step instructions of how do you do the reasoning. So we don't use SGD at all. And the bottleneck, I think, for understanding what's intelligence, what is reasoning, is figuring out how do we build like the good models of the world. Like if you have a really good model of the world, then a lot of things get easier. Like for example, it's really easy to make an aimbot in Counter-Strike if you know where's the enemy's position, right? And you just do like, yes, if I point in this direction, given like just like do like compute the offset vector, or like compute like the angular difference between like where you're looking and where is the player set, and then you can just shoot them in the head. So it's really easy if you know where the player's head is. Well, and there are more examples like that once you have a world model, many things become a lot easier. Okay, does this make sense so far, Emily?
It seems like you want an interpretable model, so that you can figure out how to change it and do what you want with it, and you want to understand its reasoning process.
Yeah, the idea is that, I mean, I didn't talk about anything like, yes, and then we align the system or something like that. But right now, basically, I'm just trying to figure out, okay, how do we do this reasoning at all in a way that we don't have this process like SGD that gives us this giant thing that we cannot understand at all, but instead sort of we know how to do reasoning. Because then, if we were to think about, okay, what are the properties of this reasoning? Like, what are the properties of such a reasoning process? Like that it won't kill us. That's probably a lot easier if you have a concrete reasoning process that you can understand. And making sure that once you figure out, oh yeah, it should have like these properties or something, or like this is actually what myopia is or something, now we can formalize it. And then it's like, yes, now we can sort of see that the system is myopic because because we just have the source code of the system, we can look at it and understand it. Does that make sense?
Yeah.
Okay. So how do we do this? So, well, like I'm like, yes, and like the bottleneck is like building a good model of the world. Like we want to have a model. Okay, here's what I imagine. If we would figure out how can I have a model of the world that is really good for planning, how to manipulate, how to reach a certain world state, and is accurate and is describing the real world, that would be really powerful, right? This is probably like, if you figured out that, then having some sort of planning algorithm that like goes through the model is probably easy. Especially if you sort of abstract your model in the right way. Like imagine you have a world model and you have figured out how to abstract it in the right way such that the kind of reasoning that you want to do can be done at the appropriate level of abstraction. Like if I'm like, maybe the model, like as an example of what the human might do is like when the human thinks, I want to have foods, then the human doesn't consider all the atoms, right, that are everywhere, but there's like some abstraction that is like food. And you can like use that to like see how could I get something that tastes good in my mouth or something. Okay, wait, this is a really terrible example. I'm not sure I have a short example of this.
So it seems like you want an AI with a world model, and it needs to be able to abstract things, to be able to communicate things properly. Is that
Well,
kind of what's
so
going on?
so here's a really nice thing that you can do. If you want to search whether there is an element in a list that's linear time complex in the number of elements in the list, right? And if you do sort the list, though, now you can use binary search, and now it's like, what is it actually? I don't know, log of n or something that's like insanely fast. Even if you like so many elements, like probably if you have like a number of atoms in the universe, elements like still can just compute it. Like that's how much better it is. And so that's an example of I have a data structure. I have some data, like the elements in the list, and now I am transforming the list such that a certain property holds of the list, which is the list is sorted, which now makes it such that the algorithm binary search, that is a lot faster, can be used. But it only works if it is sorted, otherwise it breaks and doesn't work at all, kind of. Like it might just find the wrong solution. I want to do something similar, but for the structure of the world. Okay, and I'll say more about that in a bit. But the basic idea is that
Wait, so how is searching elements in a list related to the structure of the world? Like, do you want
the searching elements in a list. So this is a prototypical example of we have some data and we want to be able to do some operation. We want to like find if there's an element in the list. So you have data and now you want to run an algorithm on the data. And I'm saying if you sort the list first, now you can use binary search, it's a lot more efficient. So sort of like if you imagine it doesn't cost anything to sort the list, then it's better to have the sorted list because the sorted list has a certain kind of structure, but it's not really that related to the world structure. It's just like there's this property that holds of the list, which allows you to run the really fast algorithm. And what we want to do is, well, maybe I can just explain now the actual thing and draw stuff on whiteboard. So the thing is, I want to do something like that with a description of the world that is low level. Change it such that it becomes easier to compute. It might be because you abstract it or something binary search where you don't really abstract anything. Okay, so like specifically here's how I would think about how I would model the structure in the world. So here's a very simple example. So imagine we are in a grid world and we can like move. I can like go up, down, left, right, 3x3 grid world. What I can do is I can write down basically what I call the world state graph is a game tree with all the vertices that are equivalent merged. So the world state graph here, it would really look exactly like the grid world. We'll make a more slightly more realistic example in a moment. But sort of like what this means, how you want. So like this is a graph such that all of the edges are labeled. I guess there are a bunch of these versions of these graphs. Right now let's just think of the graph where each vertex contains the entire world state. It doesn't really matter how you represent the world. There might be like lots of different ways to represent this world, right? You could say like you have two variables that is like indicates the x and y position, or like the two integers, or I have a boolean nine booleans, and they tell me where I am. But we always get this graph when we think about I'm in this state and now I can perform, well in this case like 3 actions. Where do I go?
Wait, sorry, what's the relationship between the left and the right one?
Okay, so yes, let me say it slightly better, hopefully. So this is a grid, right? That makes sense, right? And we can like walk around and we have like these actions. We could call them like up, left, right, down. Makes sense? Does that part make sense? And like here's our position, I guess. Like this is one way you could draw that we are in this grid world.
Okay.
So it's like if I press like left, then this thing would move here. So it would be like this. Okay, now I notice I can draw this graph a lot less confusingly by just making it explicit. So I do this, and now I have a different, because this is just now a representation of the entire world state. And now I have here this edge, which is labeled left, and then I have this edge labeled right. And these are the vertices, and they just contain the entire world state. And like here I can go like down, then I do the down action, and up if I do the up action, and then I am over here. And then I have also these other vertices here. And they are all like connected in the obvious way. Does it make sense? That's the same as this.
Oh, so it's more like, so the right-hand side is basically like what the actions you can take, roughly speaking.
Yeah,
And
the right.
then, so the edges are like the actions.
Yes, in this case, we can think of labeling them as actions. Yeah, I think that is usually what you would want to do, though there's like a bunch of ways in which you can abstract them. But I guess that's not really relevant, right? Yes, let's just think about this thing where we have also the actions. Okay, so this is a graph that completely captures this word in the sense that, well, here's a procedure that I can do to generate this word. This word is some computer program, right? It's like here's some state, here's the actions, each action corresponds to some state transition, changing world state, right?
Right, okay, so you have the world state is which position you're in, and then you can take actions and then you can create a graph of like different world states and how you can move in between them.
Yeah, you could like, for example, say like, oh, we don't see this rest of the graph. We just like, we are here in the center. And now I'm like, what can I do? Well, here's just pick a random action. And it's like, move somewhere. Okay, I moved here. Now it's like, and now you just have this graph, right? That you have these two vertices. You observe that, oh, I was here. Well, what would actually, well, okay. The thing why I didn't even draw this in the beginning. Okay, now there's a lot of stuff. Okay, briefly, I just want to say, I'm assuming here's the entire world state in here, but basically, in the entire rest of the thing that I'm going to talk about, almost, we are not going to need it. We don't even need to look at it. We don't need to understand anything of the world state at all. We only need to be able to compute whether two things sort of have some delta. Okay, maybe I should stop there. Just like as a note, because like, the idea of this entire thing is that we can analyze the structure that is in the world without needing to understand the world at all. Okay, but that's maybe too far. So like I could just do random actions and generate a graph, and each time when I notice that sort of I have a function that tells me like current state or like state of a vertex, is it equal to the state of another vertex? And so I'm just going to do like all of the actions, or like you could imagine to do, you know the game tree. You know, it's like in chess, it's like on tic-tac-toe. It's like, yes, initially here's like we don't have any board state, right? Like it's just empty, and then it's like, oh, I could place an X like in the center.
Okay.
And this is like one possible action that player one can do. And then it's like, oh, I could also place here an X, or I could place an X over here. Like there are 9 possible ways in which I can place an X, right?
Yes.
And basically this thing here is the same, only that we merge the vertices when they are the same. So in chess, if I move my horse forward and the other one player moves the horse forward and then they move the horse back, both, then it's the same state again. But instead of making a new node, we then link back to the root. That would be an example. So that's why this is not a tree. Or like it's the same as this tree, but we merge all the states with like the equality function which we somehow have. This makes sense now.
Okay, so I guess you're kind of it kind of reminds me of like a state machine where you have states and then you have actions that lead to different states. So in this case, it's like the movement of this circle in this
it's somewhat related, but it is actually lower level in some sense.
Circle over here.
Yeah, it basically describes, so like the edges describe what can I do. It's like in each vertex, I know I can do all of the outgoing edges. These are all like changes I can cause in the environment, like to the environment. It's like, yes, I could do this and then I would go to this other environment, which has a different state. That's the idea. Okay, but now here's an important thing. Yes?
Okay, but then you said something about you don't have to know everything about the world, and then you can like are you saying that we should sample actions?
Yes. The way why this is sort of useful is, I mean, this is not a good representation of the world because, well, imagine I have an infinite grid world that's like this, really easy to represent, very low description length, but this graph's infinitely large. So like we don't want to be like, this is our world model. But what this allows us to do is that we can the only thing that we have is we can compare if two vertices are the same world state. we can't look inside the world state, it's just a black box, then we can construct this graph. And the idea is that we want to sort of like, we are in some state, now we want to sort of start to explore and discover the structure of the graph. And we can sort of always do this by sort of sampling a bunch of like generating a bit of this graph and then using that to infer structure. Like here, a very simple example of this would be, imagine you're in some world, you have no idea at all about anything. Like what do you do? How do you understand what this world is? One very simple thing you can do is just try all pairs of actions and then see whether there is direct inverses, whether it's like, I have an action such that if I perform this action and then I perform another action, then I always go back. That would be a very simple example of discovering structure. And actually, I don't quite understand how yet, but somebody told me that's the case, that basically if you do that for all of the possible action pairs here, then for this thing, you literally can just infer that it's a group. And then you're like, oh, it's a group, now I can, but then it applies this lattice structure. And with lattice structure, I mean like that, but if this was an infinitely large grid world, then if you look at any vertex, it's sort of always the same. It's like, oh yeah, and any vertex, if I go left, then like, but I can go left always, sort of makes sense to talk about. I have this graph embedded into the Euclidean space, and there's like always like a vertex up, right, down, left. Okay, well, maybe that's enough on that.
Okay, so how does this relate to having a reasoning
Very good
algorithm
question.
that
So
we understand?
So what we want to do, why we do this at all, is we want to have a model of the world. Because that's really useful, right, for reasoning about the world. And the thing about this is that you give me some computer program, or like any computer program that you could think of, has a corresponding graph like this. That means any computable world has a graph like this. I mean, most of the time it's like infinite, so we cannot look at this graph, or we don't want to even store it. But like that's a really important thing, that like this kind of structure, if we sort of allow to be infinitely large, can represent any possible program. It's like, that means sort of, I have a world, and if I assume that the world is computable, which seems not like a very strong assumption, then it makes sense to talk about this graph. And what is good about this graph is like that it is sort of like how do you do program inference? It's really hard to program inference, be like, what's the actual like computer program that generates like the real world, for example, or Minecraft? If you want to just infer this based on atomic, or like based on your like pixels on the screen, that's a really hard problem. And the idea here is that, okay, we don't do like the general program search, we instead locally sample this graph which describes the program, like in a really real sense, because like if I had this entire graph, I just knew the entire program. Like there's nothing else I wouldn't know about the program if I actually had the entire graph. Like if I have this graph, for example, and this is the computer program where I can work in the 3x3 grid world, but I don't need anything else, right? Like I guess I need some interpreter that's like, what does this mean? But I could run sort of this is equivalent to the original computer program where I'm like moving the grid world. Like this is sufficient for describing it perfectly, right?
Computer inference to having a program about something is hard.
Sorry, you cut out. I didn't get the entire thing. Could you repeat that?
Sorry, my super good. So it was hard to do. So
Oh no.
are you saying that
Yes.
that's going from observations to having a computer program of those observations is really hard, that is consistent and stuff?
Yeah, that's like, well, Solomonov induction does that, in case you know that. And it is, well, I mean, Solomonov induction doesn't care about making it practical, but it's just like a hard problem. It's like, the idea behind this entire thing is that we can represent a part of the world in such a way that it is easier to analyze what kind of structure there is. A structure directly corresponds to the computer program. Like there's some, like this is evidence about what is the actual computer program. Evidence that is really easy to get. Like if for example, if like, imagine there was not this arrow here, it's now a different computer program. Maybe this wasn't a lattice, it was some other different graph. That is telling you something about the computer program. And what I want to do is I want to look at the graph, and then they have lots of nice graph and analysis algorithms, and use these to extract all of the evidence about what is the right computer program. Actually, well, that's the first step, and then you just then you infer the computer program. In a like an example would be, imagine this graph is infinitely large. Now you could be like, oh, I'm going left, I'm going up, I'm going down, I'm going right, and then oh, I go up, I go right, I go up, I go left, I go down. Oh, I'm in the same thing. And like you try it a bunch of times, and you're like, oh, look, it's always like these kinds of structures are here. Oh, it seems like this is it's just always, no matter where I am, I have this kind of structure. It's like a very simple example right now. But if you know that, then you can describe the entire world by just sort of having one vertex and saying like, oh yeah, everywhere where I am, well, it's just like there's a single vertex, and if I go left, sort of this kind of delta update happens to the environment. If I go right, this kind of delta update happens. If I go up, this delta happens. If I go down, this delta happens. And now you're actually done. Now you describe this infinitely large world. So you can detect the structure, then compress the structure into a model that you can use to infer, do prediction and also planning, which I didn't talk about at all yet. Does this make sense?
Wait, so you said that with a world that is infinitely large, through abstractions, you are able to be able to.
In this case, it wasn't even abstraction. You can also use abstractions to get better descriptions. But in this case, you simply notice that any vertex is the same in the sense that the delta, so like here it's labeled with actions. It's like, oh, if I'm here, I go left.
Yes.
That is action I can do left. But imagine this. Imagine we can compute the difference between two world states, which is kind of easy if you have like a fixed representation. If you have a dynamic representation, it's harder, but maybe we shouldn't talk about that. And then you can sort of generate the labels. Instead of using L, you label it with the deltas. And if you would do this in this graph, even if it was sort of the infinitely large grid world, you would notice, oh look, I go left. You wouldn't necessarily know that's left. But at some point, sort of, you might arbitrarily decide, yes, this direction I call left. That always, if I do the action left in any vertex, it always applies the delta. Like imagine you have the worlds represented as x equals 0, y equals 0 here. And then I go left, and then it's like x minus 1, y equals 0. And it's like, I'm going around the graph. Anywhere where I am, it's just like always, if I do left, it's always gonna be decreasing, decrementing the x position. Like if you were to figure out this pattern.
Isn't that an abstraction? Like, don't you abstract like, oh, this is the position and this is like what's happening?
But the reason why I wouldn't call it an abstraction is that, like, what is it actually abstracting? It is just like, but I have an example of what I would call an abstraction in a moment, and maybe it would be clear what's the difference. But like here, it is just like a compression, right? Like imagine I have a bit string that's like 1 1 1 1 1 1 1 1 1 1 1, and then I say like repeat 1 for 10 times or whatever. That's not really abstracting it, I would say. That is compressing it. And I'm saying like it is possible, even if you have an infinitely large data structure, you can like compress it to some really tiny thing. If it has a really nice structure like this, this is like the prototypical example of really nice structure, kind of. But it's just the every vertex kind of exactly the same, if in terms of the deltas, if you would look at them. But that doesn't really matter that much for now, the distinction between abstraction, I guess, and compression. But does this general thing make sense? Or let me just say one more example of how to think about this in general, unless you think something doesn't make sense.
So are you saying that even for like infinite world models, you can use compression to be able to represent them?
If you're a world model, not necessarily. If there's a world that is just like algorithmic information theoretic random, which means just that there is no compression, I guess. That's literally kind of what it means. But then you can compress it. Like you can have some data and then it's like not compressible, but then you can compress it.
Okay, I guess what was your point about mentioning the infinite world model and you can compress them, and how does this relate to reasoning machine?
Yeah. So imagine that you have this world, but it's now really large. It's infinitely large.
Okay.
If and imagine we only see, but maybe like here it goes further and here, but we haven't observed this yet. And now you're like, oh, I wonder what is the world like over here? Like, what is the world there? I mean, you want to know that. Like, now that's prediction, not really planning. That's a question, right? That's, if you can answer that, it's kind of useful, right? It's like, I'm doing a bunch of actions. What is the world state that I get? It could be multiple ones, right? Could I go here, then here? Or like what I mean is like, of course, like go right, and then up. So in this very simple world, we could answer this question if we had the function. So if we had really this regularity where the deltas are the same, then you can just save this data structure where each edge has some delta, and then you have a function which is like predict, which takes in sort of the current world state. Let's call this env, and it takes an action sequence, and then it just returns you what will be the final environment that you're in. Like that you can do with just this thing here. If you have this graph which is regular such that in every vertex everything's the same, right? And this for this very specific structure in the graph, this function can easily be implemented by just looking up sort of what deltas. Like you can just really easily translate this, right? Well, like imagine like right is always delta 2. Then you're like, well, I'm doing like left, or like, oh, well, I'm doing right. I mean, then I'm like, yes, it's like world state, apply this delta of like D2, and then you know where you are. You can do this. And now the thing is, well, if you're actually in this lattice graph and you just jump to any point, like yes, now you're at position 1 million, and you were never there, you only saw this. It's like, what do you expect will happen? Like a prediction that's better than nothing is that, well, if I go right a bunch of times, then I use this function to predict what's the current world state now, and then will be sort of correct with high probability than saying I have no idea. Like that's now better prediction, sort of, if you think Occam's razor is good, I guess. And so like the thing is, this is a very simple example, but remember when I said any possible computer program has a graph like this. Like the thing is, you can do something like this for any world, like also for the real world, assuming it's computable. Like then you can do this. Like you can definitely do this for Minecraft because it's obviously computable, because it's a computer program. And it might not be this lattice structure. This lattice structure is just a simple illustrative example of, oh, this is a simple kind of structure. How could we like now do stuff with it? How could we model it or something? And you might have very different, much more complicated structure, but like the idea is that we look at the structure of how does the world change. Like if I'm doing a bunch of stuff, like what does this graph tell me about how the world changes? And then find the regularity in the graph. Yeah, it is very simple to find the regularity, and use the regularity, like exploit the regularity such that, or like, well, see the regularity, then model the regularity, like this kind of thing, models the regularity here. And then it is like a really compressed representation of all the regularities, sort of compresses it as much as possible, like that, or like that's what you can do in principle. And now you sort of have a model of the world. Like, okay, maybe so
I guess, okay, so maybe you're expanding from a simple example to, oh, we can somewhat use this principle to create a model of the world. Is that what you're roughly saying?
Yes, this is a simple illustrative example of like, oh, I have the environment, I have this graph that always exists for the environment, for any program. The environment can be any program. And now I can think about doing some graph analysis to discover the structure. And this is a very simple example of a kind of analysis you might do to discover that, oh, in fact, you can describe the world like this. Ideally, sort of in the end, you want to have the algorithm that automatically sees the structure. And it's like, oh, yes, here's the structure. I'm going to model it like this. Now, and this is now describing this part of the environment, and it can be used in this way to predict what will happen if I do these things. It can be used in this way to plan how to get to a particular target world state. Like these are the things you can do. And the idea is that you start with this graph, which is really easy to generate and also sort of easy to analyze.
Have you tried expanding this graph to closer to real world life situations?
Yes, okay, let's make this graph, let's make a graph that is not the simplest possible thing.
No,
Um,
but we don't have to draw a more complicated graph, but like in practice in your research, have you tried to make a graph for something much more
well,
similar to the real world, and how has that gone?
but we can think about Minecraft. So in Minecraft, it's pretty obvious. But so you might think like, what the fuck is this structure here? Like, obviously it's so dumb. Like, nobody, the real world would never be this simple. But like,
Mm-hmm.
Minecraft's not really simple, right? Like, Minecraft's kind of complicated. Like, complicated enough that nobody knows how to write the algorithm that just randomly starts in the world and then like gets a diamond 1 hour after learning the world for a week or something, without deep learning. Nobody really knows that, probably, I would guess. Um, but
Okay, so
this
I
kind of
guess it
structure,
seems like you've tried to model Minecraft using approximately that kind of structure.
well, I mean, I didn't write like, well, okay, maybe there is some, well, the problem is I cannot draw the Minecraft graph entirely, or like even a small part, because Minecraft is really complicated. But
Right.
this kind of structure, even though you might think, oh, this is so bad, or like this is so simple, it doesn't happen in the real world. In Minecraft, it like happens very often. For example, well, the most obvious example is, of course, you move around, right? You move around, and well, if we were to think of the very simple Minecraft thing, where I'm just like I can move forward or left and right, and well, obviously it's just a grid world, and you can model it. But now, what happens if I add like rotation, or that I can strafe sideways, or move like a bit to the left or a bit to the right?
Mm-hmm.
The thing is that this kind of structure is still there. Like you can like arbitrarily like take arbitrary small steps, and arbitrary small step to the left, arbitrary small step forward, right, backwards, assuming you don't change the rotation. It will still be that. So like you can approximate it like that. Obviously, you don't want to like you want to immediately like
Mm-hmm.
abstract this away if you do that in practice and infer it, because like well, I mean you can make an arbitrary large this graph for like small movements. But like the structure is like it's just described like that. And now here it's like about rotation. What is about rotation? Rotation obviously is not this graph, right? Actually, it's just like a lattice graph like that that's embedded in a sphere manifold, I guess. Like because like I can, well, if I just imagine I can rotate on this axis, well, now I discretize it. Well, obviously it's a line graph. So that line graph is one-dimensional lattice graph. If I add rotation, well, now I could imagine I have these like points on the sphere. So I'm like going here, going up, going right, going down. Let's graph. Well, or maybe not exactly let's graph, depending on, well,
Right, okay. So
depending on
I
how
guess
you.
okay, so how does so you have a okay, suppose you do have a world model in this structure in which you can put it in the graph. What do you plan to do with it?
Well, okay, so like we don't want to have our world model in this graph, because this graph is terrible for being a world model, because
Okay.
it is really huge. Like,
Yes.
so what we want to, the thing that is good about this is that it is really easy to generate and still allows us to infer the structure, right? Like I don't, so the idea, or like for Minecraft movement, is like I move a bit forward, I move a bit left, right, generate a bit of this kind of graph. And now I'm like, yeah, it seems like I have this kind of structure. I move forward, then left, then back, then right. Oh, I'm in the same place. Seems like that's what would happen in a lattice. Let me confirm this hypothesis. Let me do it a bunch more from different starting positions. Oh, always seems to be like exactly like a two-dimensional lattice if I'm like in a flat plane.
Mhm.
Uh, you can generalize it also that if you always have one step higher blocks, then it's still exactly lattice. But well, I guess unless you somehow, but okay, it's a bit weird if you are like. But it's like most of the movement in Minecraft is a lattice structure. It's a bit weird sometimes, because well, you can like go into a cave and then go above the cave. But if you imagine it's just like a hill, then like it's just exactly a lattice, because you can compress it such that like jumping and moving forwards and just moving forwards are seen as the same thing, just selected appropriately on the context, and then probably I'm going too far into this, but then you still get a lattice, which probably I want to use a different example to illustrate that. This is probably the last thing I can manage to do. But like the idea is we just generate this graph and then we analyze it. We're like, oh, look, this graph has this structure. Maybe this is repeating, you know? If you do Occam's razor, then it's like, oh, this structure might just be always repeating. As that's the simplest hypothesis if I don't know anything else right now. So that allows you to like infer things in the world. And this is the very simplest example of what you might infer. And then we build some model that represents this
I see
graph.
a hand raise. Do we want to have Atharva speak?
Hey, yeah. Could I pop in the question real quick?
Sure.
Hi. So this might be cheating a little bit, I guess, because I was going through your Spark application and like was reading, like I've read your like a couple last long posts in the Google Doc and stuff, and I was like, it seems really cool. Like if I'm not mistaken, the entire idea is sort of like the breaking down the world into like into really nice boundaries so that you can analyze it in an information efficient manner in some sense. Would that be correct? Is that a
Maybe
no?
you mean the right thing, but it doesn't map precisely to something in my head when you say that. But maybe you mean the right thing.
Okay. I guess so. My question was, so I'd stumbled on the neural network thing that you mentioned, or the idea that like if we have a neural network to classify MNIST, it's doing something really complicated and it's not very interpretable. And like it seems sort of hard to classify, like to translate those handwritten digits into some sort of like structured, orderly manner, like we're talking about here. Like the goal is to get to like fully interpretable models in some sense.
Mm-hmm.
So, and I didn't quite understand like how that fit in the picture. Like how would we deal with these sort of weird things that can't really be handled with nice interpretable means, or at least like at first glance. Does that make sense? Is that a bad question? Or
And so this algorithm would work if I expect that if I were a lot farther than I am now in figuring out this algorithm and had a lot more structure detection stuff, it would be able to do the MNIST thing.
okay,
Like
interesting.
this, I mean, this is like you can do this with any computable world.
Okay.
And obviously, like you can have a world where it's like somehow you can encode the task of predicting MNIST into like a world. But I mean, just the default thing where you have like here's my loss function is sort of a world, and then like the agent just says a digit. Like that's just a computer program. Like okay, the thing is, so like any computer program, if you draw the world state graph on it, it would just be a line graph because it's deterministic. Let's assume we don't have any outside randomness.
Naturally.
So any computer program is like just like as I do this step and then I go to this state. I mean, at some point it might loop around. It might either be like this or without this like loop and go on forever. But that's the only two possibilities. If I have a computer program that's just deterministic. So what we're doing here is we add sort of a function into the computer program, which is ask agent, which just returns an integer according to like assuming you have a fixed number of actions, like 10 actions. This function just returns an integer. And then like, well, the program does something with the integer. Or like, I mean, I guess could do nothing with the integer, but that would, but then you would get this graph or the infinite line graph. Or
So are you
terminates,
saying
and then it's finite.
that it's the MNIST neural network can be modeled in this structure because it's deterministic?
Well, this can model any computer program. So yes. Yes, I probably failed to communicate the important point. But this can just, give me some computer program, like this is as a graph that corresponds to a computer program. Usually it will be so large that you can't write it down, but there's always this graph that I can at least partially generate. Doesn't matter what's the computer program. So like, I can have a computer program that is, ask the agent, what is this number? But I guess you somehow want to give the agent like, you want to pass it like this is the current state of the world and you did this action, now you got to this state, and then you have like a classification function, and then you like then you move like to the left if you get like a bad prediction or something, and you like sort of sum up the score of the agent, and then that gets worse and worse the more it gets wrong, and then the agent like learns like look, this graph is such that if I'm doing this kind of thing, I'm going to the left. If I'm doing this other kind of thing, I'm going to the right. And then you can say like, please agent, go to the right as far as possible. And then it's like, oh, the prediction accuracy is as good as possible. But only like the world state graph might be not actually a line. That is like there might be other variables that you want to give your agent about the world, but like there will be some dimension in the graph that corresponds to like the loss going up or down, and then you can say, please sort of walk on the graph in that direction as far as possible, and that would then mean the loss is as low as possible, for example, or as high as possible. Like the thing is, you can also, like this thing about this thing is, also can say like, please make the loss exactly like 3.789, and then I would do it.
Interesting. Okay, so I kind of can tentatively agree with that, but if I could follow up real quick, I guess how human interpretable would this condensed version be, this condensed graph, or like would it really make sense to humans looking at like,
Uh,
oh, like what one step here, one step there does for something like MNIST, for instance?
So
Or is there
you
some,
would
because I assume there's like,
obviously, so
yeah,
like there are a couple of things. Obviously, you cannot understand the entire world model if it models the entire world at the low level or something like that. Like, I mean, obviously, you cannot understand the entirety of this graph because this graph is possibly infinitely large. Well, okay, I guess you're talking about the compressed version of this graph. But, well, I could not talk about this now for 1 hour probably. I expect this would be interpretable. I don't have said anything here that tells you anything about why this would be, I guess, interpretable, besides that this is something where you can understand the process that you're going through. But basically, I think there's lots of, like, okay, here's the thing you can definitely do. There might be an indicator, which is not what the final system would do. But if I'm like, I have an algorithm that detects whether I'm in a lattice graph. I have an algorithm that infers what are the translations in lattice graphs such that I can completely describe the entire lattice graph. If you have some infinitely large lattice graph, then obviously it's super interpretable, right? Because you're like, yes, look, the algorithm that detects if there's a lattice, said there's a lattice, then it inferred this structure which describes a lattice, which of course we know because this was the algorithm that was run because it was detecting that there's a lattice. And then you're like, aha, this is a lattice, which means it will just tile everywhere. And that's what this means. So like in this case where you actually have the algorithm sort of hard-coded, then it would be like, I mean, couldn't really be more interpretable in some sense. If you have the algorithm that would infer the kinds of structures that exist, then that's still a lot more interpretable, I think, than, well, like what you get is that, well, obviously the model needs to like know what is the structure, so it needs to infer what's the kind of right data structure that captures the structure, and then you're like, look, here's specification of what's the kind of structure that can describe this environment. Like it might be a lot more complicated than this. It might be like, yes, if I go to the right, it's not always the same. It's actually like depending on the function, depending on like some part of the world state or something. Maybe you would need to describe it like that. But this would be sort of like if you figure out the structure inferring algorithm that figures actually out the structure it can describe, whatever structure you're seeing, somewhere this algorithm needs to write down what's the structure. And that seems like really not very hard to make it such that you could look at it and be like, oh, look, it's this structure.
that
But
sort of
basically, I'm not
makes
thinking about this at all right now because I sort of expect this to be kind of easy if you figure out any kind of algorithm really, where you just write down the explicit source code and you know every step how it works, then if it sort of infers certain kinds of data, well, I guess the only thing I'm trying to do is like, yes, if you have the algorithm that infers the data structure, you want to make it such that the algorithm that the inference steps are sort of, like you understand sort of the process of how it infers the data structure, and you understand sort of what is this data structure, like how is it constructed. Like that's completely different from neural network, right? Where it's like, yes, here's like this thing, it can represent anything, let's just update it sort of, and then we get something. But here it's like, sort of if you don't even try to make this interpretable at all, but you follow this approach where you try to write down explicitly and like, oh, now I have this data structure and do this thing and this represents that, then by default it's kind of interpretable. Okay, one thing that's kind of important, I think, which I didn't think it would take so long to get to there, is this is so far it was really this super simple structure that is like, like obviously this doesn't work in the real world. Like in Minecraft, the entire graph is not like this. There will be sort of subgraphs that are like this. But sort of an important insight is that we can just make these structures. And that's a bit what I meant in the beginning with the binary search thing. Like this structure, I didn't talk about it at all so far, but like this structure is really nice for planning if you have the deltas being regular, because then you can basically, then you can be like, okay, what's the delta to this state? And then you're like, just greedily doing the actions that would get you closer, and then like that just works basically. So if you detect the structure that's really good and like bounded to like, oh, Minecraft, like what if you detect sort of, oh, right now I'm in this kind of lattice thing, then it's really nice because it's really easy to compute how to get to a particular world state in the lattice. But we might not have the structure. So like sort of the thing you can do is you're given this graph, some graph, but it is not this lattice at all. And you can sometimes take this graph that you're given and transform it in such a way that you don't lose any information, meaning that you can sort of like translate back to the original graph if that's necessary, but you get a structure that's nicer. For example, this structure, which is like kind of the nicest structure you could have. And a concrete example of this would be if you're in the grid world where you don't only have a position, but you have a rotation. And now the actions would be like you can turn left, you can turn right, or you can go forward. And if you draw the graph, so like here's a nice thing. It's like this graph is so trivial that like it doesn't tell you anything interesting sort of about this, because it's like so obvious that this is the graph that describes things. But if you have the thing where you can be rotated, then you can draw this graph and you can immediately sort of see by writing it down, I guess, is by writing it down in a particular way. But okay, it's a bit confusing. But if I would write it down now, then you would just immediately see the structure. But it's a bit misleading to say then, yes, it's really easy to understand, because always when I write down the graph like this, like I did on the left, I'm sort of always adding additional information by having an embedding. And I just write down the embedding such that it's nice to see the structure. If I would place the random randomly, then it would be, of course, not so nice. But I'm basically claiming that that niceness is also what that the niceness of this formalism of we have the graph and we analyze it and look at the structure would also still sort of be nice for an algorithm that just would look at a list of edges and vertices that would describe the graph, though probably slightly less than if I just draw the embedding, which already shows the structure. Okay, but this thing is basically like this. So we can be in the center and we can look up. We can be in the center and we can look to the left. And we can be in the center, look to the right. And we can be in the center and look down. And, well, I can move between all of these states. And now, this is just describing the rotation for the center point. There is, of course, also I can be rotated like this in if I'm in the right thing. If I'm over here, I could be like, okay, let's see, this thing was like facing to the left. So let's say I am facing to the left here. Here I'm facing to the right. And basically I just draw exactly the same graph, only now the graph has the rotations adjusted, the position changed. And we have like, well, I'm just not going to draw both arrows. This is exactly bidirectional. And now we also get the thing that like this thing goes over here, this thing goes over here. And you always, if you're in this thing and you move, for example, up or left, you always go to like sort of the opposite vertex. And so like here you would have like, again, these four things, and this would go over there, and this would go over here. Okay, it gets too messy, and then we basically have, so we have like these, we have like nine of these if you think about the 3x3 grid world. And these are like all connected, and that's like really messy, and you don't really, or like, because I'm writing it down like this, it's really easy to see the structure, of course, that yes, you have this thing, and this just always repeats, except that the position is like different. But it's, but here's the thing that I can do. If I have an edge regular lattice, I mean a lattice, if I just have a lattice, and I have this graph, then the obvious thing I can do is I just like, for every vertex that I have in this graph here, G, I just replace, place in this graph in there, and then I need some function that maps sort of the edges that I have here to some vertex in here, which would be this thing where I'm like I have an edge coming in from here, then maps like to the up vertex. So like if this was like going up, then this would map it to this thing, and so on. And this would just describe the entire environment. And now I have a lattice graph, which I can sort of use to plan now. Like what I can do, very roughly, is I can first sort of detect there's a lattice here, okay? Extract the structure of the lattice, extract notice that this is like this lattice, and then I can use my nice planning algorithms on this lattice and compute like, oh, how do I get here? Which is really easy. But it's like here, it's like completely, well, like how do you do it here? It's like you need some. I mean, obviously BFS would do it, but we don't want to use BFS because it's like if you have this world state graph and it's really large, we don't want to do that at all, ideally. But we just want to analytically compute the solution. And in the Let's graph, we can just do that. So we can just do the planning here, and then we sort of know. By sort of, you can imagine you have a planning algorithm for this part that allows you to compute sort of how do I get to any vertex in here, and how do I jump out of it, sort of, such that I get to the next vertex. I can describe this, obviously. And then you just say like, oh yes, to go from I can go from here to here, and that takes. Therefore, I need this sequence of edges, which is easy to compute because it's a lattice graph. And then each time I'm like need to like compute how to get from some specific state in here, like in here. How do I get from here to like here? Then you're like, yeah. Then I just look at the lower level graph, and then it's like, oh yes, I just go there. Which in this case could just make it the lookup table because it's like tiny. If you have a larger thing. But might be a really large graph that still has some structure. Like this is all of this is composable in the sense that like, oh yes, you have some structure that you handle here, and then you abstract it like here, and then you might even abstract it to multiple levels, get multiple lattice graphs or something, and then you have an abstraction that's basically that's the kind of thing I was trying to hint up in the beginning, where you have the list that you sorted. Now you can use binary search, which is an algorithm that's really good. Because it's really fast. And this is now the same idea here, that we convert the graph into structure such that we can use the nice algorithms that we have.